All right, so this is sort of the opposite of the first lecture in topic, although there will be some overlap in method, as we'll see at the very end. My notes here. Okay, so the question for today's talk is how large can prime gaps get rather than how small. So there's sort of two questions here, so upper bounds and lower bounds. So on the one hand, there's sort of the upper bound question. Okay, so we are interested in upper bounds in the prime gaps that are true, which hold for all n. So what's the best upper bound we can get on these gaps? These gaps are very irregular, and occasionally they are quite large, sometimes they're very small. And so we're also interested in lower bounds. Which hold for infinitely many n. Okay. It's not interesting. We don't really interested in lower bounds, which hold for all n, because we expect from the Trim conjecture that the lower bound only for lower bound is 2. All right. So we can start with the upper bounds first. So last time we talked about use Bertrand's postulate. Bertrand's postulate is a classic result in elementary number theory. It says that every long interval, x2x contains a prime. Any x bigger than 2. And so this already gives a very simple upper bound. Okay, prime gaps are never bigger than Pn. You can do better with the prime number theorem. There's a number of primes up to x is equal to the log integral plus the low order term. Okay, so the prime number theorem, it's easy to see. You can apply it for x and x times a small, say 1 plus epsilon, and you can get a generalization of Bertrand's postulate that for every epsilon, every interval of the form x, 1 plus epsilon x contains a prime. If x is large, sufficiently large, depending on epsilon. It's an easy consequence of the prime number theorem. And this tells you that Pn plus 1 minus Pn, the prime gap is less than epsilon times Pn if n is sufficiently large. Depending on epsilon, or in more compact notation, the prime gap is actually literal O of Pn. All right. And then with better error terms in things like prime number theorem, you can do better. So, for example, if you know the Riemann hypothesis, this tells you that the number of primes x is in fact the log integral and the error term is actually not just literal O of x over log x, but actually x to a 1/2 just literal of 1. And this gives you, okay, if you work out, it tells you that in fact quite short intervals contain primes. If x is large enough. Okay, and this tells you that the prime gap is in fact bounded by Pn to the 1/2 plus something's literal of 1. And in fact, if you are a bit more careful with the error term and do everything to optimize as much as possible, you can bound this by a constant Pn times square root of log Pn. Again, this is about a Cramer, like 1930s, I think. And this is still the best bound that we know, even assuming the Riemann hypothesis. Now, this error term is not, yeah, we don't have this. We have improved this error term a little bit. I think the best error term we have currently in the prime number theorem is something like x times the exponential from memory side log 3/5 x over some log factor, which I don't remember, or something. And so you can get a little bit of improvement, but you can't get anywhere near as good as this. Nevertheless, even without the Riemann hypothesis, it was shown by Baker, Hamann, and Pintz in, I think, the early 90s, maybe, that we can't quite get intervals primes in this range, but we can get primes in this range. So 0.525, there's a large constant such that any interval of this form contains a prime. For C large enough, and this gives us the current world record for the size of prime, upper bound prime gaps. So we can't quite get 0.5, we get 0.525. Okay. By the way, I'll mention there's a famous conjecture of Legendre, just as a little side note. Legendre's conjecture says that between any two consecutive squares, this contains a prime. Okay, so any two consecutive squares should contain a prime. And so this Riemann hypothesis result almost gets you that. If we could get rid of this plus epsilon, we could basically prove Legendre's conjecture. But right now, this conjecture is open, even assuming the Riemann hypothesis. So this is quite a challenging conjecture. It is roughly equivalent. Sorry, it's roughly equivalent to the prime gap being bounded by the square root of here. I can kind of tell you a little bit about how this is proven. So it uses sort of very classic analytic number theory, in particular the connection between the primes and the Riemann zeta function. So it's not really the focus of this talk, but since it's so standard, I think, and maybe not everybody has taken a course in analytic number theory. Maybe it's just nice to spend 5 minutes saying why the primes are connected to the Riemann zeta function. It's a little tricky, but now quite standard. Okay, so yeah, so the connection between the primes and the Riemann zeta function, which is this funny function summing over integer yes. Strictly speaking, this series only converges classically when S is big, but there are tricks to extend it for other values of S too. Okay, so the connection comes from the fundamental theorem of arithmetic, ultimately. So this says that every number n is the product of primes, some prime p1 to some power a1, p2 to a2, and so forth. In exactly one way. Another way of saying this is that every number is the product of all the primes that divide it, but each prime has to be expressed by the number of times, but the primes have a pure multiplicity. So if there's a prime power that divides n, you have to that prime appears multiple times. So one way to say that is that any natural number n is also the product of all prime powers that divide n of p. Okay, so for example, 12 is 2 times 2 times 3, because 2 divides 12, 2 squared divides 12, and 3 divides 12, and it was all those numbers together gives you 12. Okay, so this is another way of saying the fundamental theorem of arithmetic, and so this is a product, but you can turn it into a sum by taking logarithms. And another way of saying this is that the log of any natural number is the sum of all the factors of n times a little quantity called the Maynard function. And the Romangold function is defined to be log of p when d is a prime power and 0 everywhere else. Okay, so log 12, for example, is log 2 plus log 2 plus log 3, which is lambda of 2 plus lambda of 4 plus lambda of 3. Okay, so so this is a function that detects the primes. It's basically a weighted function. It's almost the indicator function of the primes times a log factor, and then you also have to, there's a correction factor from squares of primes, cubes of primes, but those are lower order. It's basically a weighted version of primes. In the language of Dirichlet convolution, this identity is telling you that the log function is the Dirichlet convolution of the Romangold function and the constant function. This is called Dirichlet convolution. Okay, the Dirichlet convolution of two functions is defined to be the sum of all divisors. So I was dividing n f of d, g of n over d. So it's an operation which is like a multiplicative version of ordinary convolution. Now, in Fourier analysis, every time you see an identity that was convolution, you are very, very tempted to take a Fourier transform of that identity because that turns convolution into multiplication. And there's a similar trick here. So once you have a convolution identity, you can often get a lot of mileage out of it by taking Dirichlet series, which is a multiplicative version taking Fourier transforms. Okay, so this identity tells you that for any parameter s, and let me not worry about convergence issues for now. You can deal with this. If you take the Dirichlet series of this quantity, then this is, you just plug in the identity. Then you can rearrange this. You can write n equals d times m. And you rearrange this, and after just a little bit of work, you just use Fubini's theorem. This Dirichlet series of a convolution factors into the product of two individual Dirichlet series. Okay, and this you recognize as the zeta function, the Riemann zeta function. This with the log, it's basically minus the derivative of the zeta function. Differentiate the zeta function term by term, basically get this. And so what this tells you is that the Dirichlet series of the Romangold function is minus the log derivative of the Riemann zeta function. And from complex analysis, you know that this function has poles depending on coming from the poles and zeros of zeta. So zeta, for example, has a pole at 1. And so the pole at 1 will give you actually a simple pole at 1. But then zeta function also has zeros, and every zero will give you another simple pole of this log derivative. So actually, you should get the sum of all the zeros of the zeta function. So by this row, you sum over all the zeros, you should get some sort of contribution coming from all the zeros. And then maybe there's some low order terms coming from the Hadamard factorization theorem. Okay, so if you want to justify this formula, zeta is almost an entire function, and you can factor it into its zeros using the, for example, the Hadamard factorization theorem, and you can get identity like this. Again, I'm glossing over the issue of exactly how to make the series converge, but that's a technicality. And then it turns out that you can invert this formula and try to solve for Romangold function, and the traditional way to do this is by a residue theorem calculation involving what's called Perron's formula, which I won't do here. So let me just say that by using sort of contour, complex analysis methods, okay, say Perron's formula. What you get is you get what's called the explicit formula. I think of Riemann and Romangold, that if you want to sum the Romangold function up to x, this is going to be, so there's the contribution coming from the pole at 1, which turns out to be x, and then every zero of the zeta function gives you a contribution. Turns out x row over row, and then there's some lower order error terms coming from the error terms over here. So there's a way to sort of transform this identity into an identity like this. And this is basically counting how many primes there are to x with a log weight. Yeah, so sort of roughly, you should think of this as the number of primes up to x times log x. That's kind of roughly what this is. It's a little, it's slightly, it's not exactly this, but this is roughly what this is. And this is where the prime number theorem comes from. This is why the prime number theorem, number of primes up to x, is like x over log x. But then you have all these extra terms coming from zeros, and you need to deal with them. And so the best case is if all these zeros, so the size of these quantities depends mostly on the real part of rho. So the best case scenario is if all these zeros lie almost for the critical line, where all the root part is 1/2, that would make each of these terms have size root x. And then you have to sum the series and so forth and play some more games. But basically, once you have this Riemann hypothesis, then that's kind of where this x1/2 error comes from. Now, we don't have the Riemann hypothesis. Okay, so what we know is that the zeros of the zeta function, yes?
The formula, so we have rho on the right, where is it on the left?
Oh, rho is summing over all the zeros of the zeta function.
Okay.
So the zeta function has a bunch of zeros. Actually, technically, you have to divide the zeros into two categories. There's the what's called the non-trivial zeros that lie in this. This microphone has died.
Yeah.
Is it? Oh, not? Okay, no, it's back. Okay. Yeah, so the zeta function has zeros, which historically are always called rho. Yes? Yes. So every zero contributes one term to this formula. Yeah, there's also some extra zeros called trivial zeros that they're negative even integers, and they sort of contribute an extra error which is quite small, like log x, which I'm sort of suppressing here. Yeah, basically each zero causes kind of an oscillation in this formula. This formula is sometimes also called the music of the primes. Because these zeros are complex, this actually these terms actually oscillate in x. Actually, they oscillate in log x. They look like sine waves, and so this formula is basically expressing the error in the prime number theorem as a superposition of these sinusoidal waves, and it's sometimes called the music of the primes. There are even sound files which try to play this music. It doesn't sound very good, fortunately. All right, yeah, but the sort of the amplitude of these sine waves is related to the real part of these zeros. So the larger the real part of the zeros, the louder the contribution, the more it oscillates, and the harder it is to actually control how many parameters there are, in an interval. Like for example, x to plus s power of x. So unfortunately, there could be zeros that are very, very close to the right edge of the strip, where the real part is close to 1. And they cause a lot of trouble. But the reason why Baker, Harman, and Pinch were still able to get a result is because even though we don't have the Riemann hypothesis, we do have what are called zero density estimates. Okay, so these are upper bounds on the number of zeros of the zeta function with real part bigger than some threshold sigma, and the imaginary part, let's say between minus t and t, for some large t. So if you create these little rectangles like this, and sigma is something between 1/2 and 1. So you make these little rectangles where the real part is to the right of 1/2, and the imaginary part between, say, minus t and t. There are non-trivial bounds of how many zeros there can be in regions like this. And so while there are a few terms that are quite large in this sum, there's an upper bound on how many of these terms there are. And so basically what Baker, Harman, and Pinch did is they took the best zero density estimates that are available, and use that to control the error terms extremely efficiently. And there's some other tricks as well. That's basically where these tools come from. And so, ideally, the number of zeros in such a region should be 0. There should be no zeros at all in this rectangle. This is, that's what Riemann hypothesis tells you. But there are some non-trivial upper bounds on how many zeros, and that's not as good as the Riemann hypothesis, but it's a reasonable substitute. And that's why instead of p to the 1/2, we get p to the 0.525. Okay, so that's kind of a digression. So that's showing where classical and number theory comes in. Okay, but this 0.525 is the best found known. Okay, but you can do better with heuristics. Okay, so we saw last time how you can predict, for example, the twin prime conjecture with random models, even without making things rigorous. So there's a similar calculation that Cramer did. So we can again have this work with this Cramer random model where we assume quite unreasonably that the events of different numbers being prime are all independent. This gives you a very nice prediction. So the Cramer random model, so Cramer did a calculation in the 30s. And so based on this model, he predicted that you should actually have an upper bound much better than root log n. So log squared Pn. So for every epsilon, you should get a bound which is 1 plus epsilon times log squared n for all large n. And conversely, actually, and this should be the right range of growth, that in fact, it gets at least as big as, say, 1 minus epsilon times log squared Pn for infinitely many n. And he did a probabilistic analysis. So I'll just explain the upper bound. The lower bound is set as an exercise in the notes. Okay, so again, we take a big interval x to 2x. Okay, so if you want to show this type of bound, what you're basically saying is that every time you take an interval of size 1 plus epsilon log squared x, what we're saying is that every interval of this type, let's say little x plus 1 plus epsilon log squared x, we want to show that each one of these intervals contains a prime. Okay, if we can show that all these intervals contain primes, then the prime gap cannot be larger than this 1 plus epsilon log squared x in this range, which is basically the same as this estimate here. Now, how many intervals are there? Okay, so little x can range between x and 2x, and you can make it an integer. So there's basically, so there are about x many intervals, because there are about x intervals of this type. Okay, now, given any one of these intervals, what is the probability? If you take a random model, what is the probability that a given interval has no primes? Okay, so heuristically, the probability that a single interval so this is an interval that contains 1 plus epsilon log squared x numbers. The prime number theorem says that the probability that any given number is prime, the probability of being prime, is for 1 over log x. So if I pick a number at random, the probability that it is not prime is 1 minus, it should be something like 1 minus 1 over log x. And if all these numbers are prime with independent probability, you would expect that this probability should be the probability that this entire interval has no prime should be the probability that any individual element is not prime raised to the number of elements. Okay, something like this. And this is roughly e to the minus 1 over log x. So this is roughly e to the minus 1 plus epsilon log x, log squared x over log x gives you log x. So this is like 1 over epsilon plus epsilon. Okay, so this is somehow the probability that a given interval is free of primes, 1 over epsilon plus epsilon. But there are x many intervals that you need to check. And so the probability that all of these intervals have no primes, you can bound by the union bound as x over x1 plus epsilon, and that's something that goes to 0 as x goes to infinity. And in particular, as you if you make x power 2, this is a summable sequence. So by the Burrow-Cantelli lemma, you should expect almost surely that only this event should only hold finitely often. And that's kind of where he was led to this prediction here. And a similar analysis gives you lower bound. Okay, so all right, so the prime gap should be log squared x. Now he was using the simple Cramer model where every single event number had an independent transform prime. We know that this is not quite true because of parity and so forth. And so Granville later introduced what we call the Cramer-Granville model that we also talked about last time. And that you will find in analysis actually the fact that the primes are a little bit irregular, mod 2, mod 3, and so forth, does create a little bit of a distortion. So he was led more refined prediction actually that this sort of naive count is not quite right. What should be the case? This constant 1 should be replaced by a slightly larger constant. Okay, so he conjectured actually an improved lower bound. This is Euler's constant, and this number is something like 1.12 something. Okay, so the lower bound should actually be 12% bigger than what the Cramer-Granville model predicts. Granville did not actually make a conjecture as to the upper bound, but it's widely believed that even though this constant 1 is not quite right, what should be the case, this is sometimes also called the Cramer conjecture, is that the upper bound, the gaps should grow like log squared here. Okay, if I have time, maybe I'll explain why, where this comes from, but I think I will, in the interest of time, I'll move on for now. Okay, so that's the conjectured upper bound, log squared. So now let's talk about lower bounds. Okay, can we generate large prime gaps? So there is a Pidgeonov principle argument. Okay, that tells you that the prime gap should be at least as big as 1 log Pn infinitely often. So we want to get log squared Pn. What is easy is 1 log Pn. And again, this is just the Pidgeonov principle because if you look at an interval like x to 2x, there are about x over log x primes in here. So there's about x over log x prime gaps, and the total sum of these prime gaps is pretty much x. And so just by the Pidgeonov principle, one of the gaps has to be large. It has to be of size x divided by x over log x, which is basically this log Pn. So this is what the easy bound coming from the prime number theorem. And we already saw last lecture that there's also a similar Pidgeonov principle argument because an upper bound like this infinitely often. And so there's a lot of work to improve the upper bound and get smaller and smaller prime gaps. And there was similarly some work to get to try to push in the other direction and try to make this bound bigger. And so there's a long series of works in the early 20th century where they started adding log factors or log factors to this to try to get from log Pn to log squared Pn. But this turned out to be extraordinarily difficult. So after a long series of works, Erdős had a paper, Vizintius, and finally Rankin. So in the 1930s, Rankin was able to improve this, but he got stuck at a weird place. So what he was able to show is that you can bound this by log Pn times log Pn log Pn divided by log Pn squared. Okay, and there's a series of 3 other things between this and this where there's other combinations of logs and triple logs, but this was the the best bound that he could get this infinitely often. And then people got stuck for about 60 years. No, about 70 years actually. I think yeah, 80 years actually. Yeah. So, well, ranking through this with a certain constant, and for 80 years, this funny bound, the only thing that happened was the constant got slightly larger. In fact, the situation was so ridiculous somehow that British at one point offered a large prize. He offered $10,000 to anyone who could improve this bound by anything bigger than a constant. He could actually get this to be a better bound. Now, this is still quite well short of log squared here, because all the factors here are only double log at best. So in about 2016, 2014, this bound was finally broken by work. Well, there was first two papers. There was a paper of Kevin Ford and Green, Sergei Konyagin, and myself, and independently by James Maynard, and then we combined forces to get to optimize all the bounds. So it's a series of 3 papers culminating in a joint paper where what we do is that we move the square. That we can actually, yeah, so we couldn't improve the log or anything, but we can at least get rid of one of the logs. But that was extraordinarily challenging already. And in fact, this, I believe, is the limit of all the methods that we have right now. So, yeah, so we never collected on the prize because British died well before our work. But I also will offer the same prize, $10,000, anyone who can improve beta growth beyond this. And I really think a completely different idea is needed. Okay, but I can tell you the ideas that got us to this point. So how do you create large prime gaps? All right, so first observation is, I mean, this is almost a tautology, but it's an important tautology. Okay, so to create a large prime gap, is the same thing as creating a consecutive sequence, creating a long consecutive sequence of composite numbers. Okay, if you can find a long consecutive string of numbers, each of which is divisible by some prime, some small prime, then these are composite numbers, they're not prime, and so the 2 primes that surround that string create a large prime gap. Okay, so the problem is about how to generate strings of consecutive composite numbers. Now, there's a classic construction, which sometimes you can see in high school. If you take a factorial function, and then you shift it by, you take a large factorial, and you take the consecutive numbers n factorial plus 2 and plus 3 of n factorial plus n, you can convince yourself that these numbers are all composite. You know, so this number is divisible by 2, this number is divisible by 3, the next guy is again divisible by 2, just because every number between 2 and n is divisible by some prime, which also divides n factorial. And so this already gives you a fairly long sequence of size n of composite numbers. Unfortunately, these numbers are quite large. So because n factorial is quite big, it's like n to the n. Yeah, so you want a long sequence of numbers that are not too large. Okay. Okay. If they're too large, you don't get a very good gap on the prime gap because then Pn is very big. If you plug in Stirling's formula and you work out what this construction gives you, this actually gives you quite a weak bound. This only gives you log Pn over log Pn, which is actually worse than the Pigeonhole principle bound. So this is enough to show that at least the prime gap goes to infinity, which is not entirely obvious. But this is one bound. You can do a little bit better here because n factorial is overkill. You can actually, the only reason why we choose n factorial is it's divisible by all the primes that divide up to n. But that's not the smallest number that does that. You can just be a little bit smarter by taking the same string, but instead of n factorial, you use what's called the primorial, which is the product of all the primes up to n. Okay, so rather than multiply all the natural numbers up to n, just multiply all the primes up to n, and that's good enough. That's a smaller number, and if you work through the computation, you at least get rid of this log. and actually you recover exactly the original bound this way. Okay, so this is sort of the easy construction. So why does this construction work? Okay, and so the reason why this construction works is because this interval from 2 to n, yeah, so this construction works because this interval could be covered by one residue class. Or P for all primes P up to n. You see, with this interval here, the even numbers 2, 4, 6, 8, and so forth, they're covered by the residue class 0 mod 2. So everybody here is divisible by 2, and then when you add P to it, that number, everybody there is also divisible by 2, so it's composite. And then there's also 0 mod 3, which covers 3, the modulus of 3, and then that creates another bunch of composite numbers, and so forth. And if you take 0 mod P for all the primes up to n, these residue classes cover this entire interval, and that's what's making all these numbers composite. So you can abstract this observation. Okay, so more generally, if you can cover, let's say, the interval from 1 to y is covered by residue classes, by one residue class, AP mod P, for each P up to X, this creates a string of Y composite numbers. Size roughly comparable to the primorial of P of X, which is roughly by e to the X, actually. The prime number theorem actually lets you compute this primorial. It's roughly the exponential of X. And the reason for this is the Chinese remainder theorem. You see, once you can cover an interval like this by a residue class, not necessarily 0 mod P, but maybe 1 mod 2, and then 1 mod 3, and then 2 mod 5, and so forth. If there's some residue class mod prime for every prime up to X, then what you can do is that the Chinese remainder theorem provides for you a number n, let's say between P and 2P, such that n is equal to minus AP. You can cancel the shift by finding a natural number in this range whose residue mod P is the negative of whatever residue class you're using to cover this interval. And then as a consequence, if you look at the numbers n plus 1 up to n plus y, all these numbers are composite. Because every number between 1 and y falls inside one of these residue classes AP mod P. If you add it, if you shift that number by a number which is minus AP mod P, then it's divisible by P. It will be composite. And so every one of these numbers is composite. And this gives you a large string of integers. So once you have the observation, the question now becomes a covering problem. Okay, so the question is, so with this observation, the question is, what is the longest interval? One to y, covered by one residue class. On P for all primes up to X. So for any given X, so for any X, what's the largest Y, such that you can cover the interval from 1 to Y by using one residue class mod X. The way I like to think about this is that there used to be these county fairs where there'd be like these ducks going around on a treadmill, and you have a shotgun, and you try to shoot all these ducks, and if you can shoot all the ducks, then you get a prize. Right? And so maybe you have a weird gun that on your first shot can knock out one residual class mod 2. So maybe knock out all the even ducks or the odd ducks. And then the next time you fire, you can knock out either the 0 mod 3, 1 mod 3, or 2 mod 3 ducks, and so forth. Okay, and then you keep firing until you run out of primes. Okay, and the question is, what is the largest string of ducks you can shoot with this? And so, what's the biggest prize you can get out of this game? Right. So, for instance, what we saw was that okay, one or two doesn't really matter, but we saw, for example, that if you wanted to just shoot X ducks, you can do this. Okay, using the 0 mod P residue classes. Okay, so you just keep shooting at 0 over and over again, and it will annihilate all this. So that will give you Y upside X, and that's what corresponds to this sort of log n. So it turns out that you can actually get you can shoot more than X. You can get Y as big as X log X log X over log X. Okay, you can gain some additional factor. There's some slightly larger interval of than X for which you can actually shoot everything, and that's what gives you this funny bound which I've erased. Okay. Okay. So basically, the question is, how can you sort of shoot efficiently? Okay, like you could try random shooting, sort of maybe. Well, I'll get to that in a little bit. Okay, so the right, so how can you sort of efficiently do this covering? So there's a couple tricks here. So the first observation is that it suffices to cover most of. So in the sense that in the sense that with so suppose you're playing this game and you're shooting all these ducks, and you're trying to get rid of every single duck from 1 to Y, but maybe after you do all this, residue class mod 2, mod 3, all the primes up to X, you only you get rid of most of the ducks, but there's about X over log X ducks remaining. So then what you can do is that you just buy a bit more ammunition, and so instead of going prime up to X, you ask to go prime up to say some constant X, like 100X. So that gives you a lot more primes. It gives you about X over log X more primes. And now you just aim carefully. Okay, so each new prime that you have now, you just choose one of your surviving ducks and you shoot it by just picking the residue class that duck lies in. And so if you have about X over log X survivors, you can just spend create X over log X more primes and just very inefficiently just use each progression residue class and just knock out one survivor. And that just increases X by constant, which in the grand scheme of things doesn't really make much difference. So it's really just a matter of getting so if you can eliminate sort of 99% rather than 90% of all of your elements of this progression, then you can just sort of finish things off by this sort of greedy algorithm. Okay, so this is an easier task because now this is a bit more so now that we lost some survivors, you can maybe try to do some sort of probabilistic method. So you can try some random method where you just sort of randomly choose different residue classes, mod 2, mod 3, and so forth. And if you do that, what you find is that the random method still only gets you about Y, about the same size as X. It doesn't get you better than the original back. So you have to be smarter than just than doing things randomly. You can do sort of a super autosony type thing, always taking the 0 mod P residue class, but that also doesn't really work. So, for example, if you take elements 1 through Y, and you remove 0 mod P or primes up to X, what you're left with, if Y is a bit bigger than X, okay, so first of all, the number 1 survives. But that's just one survivor. But then you also get all the primes between the y and x, or x and y. Okay, if you remove 0 mod p for all the primes up to x, so you remove everyone who's divisible by prime up to x, the only things that are left are primes that are bigger than x. And this y is going to be only a little bit bigger than x, is less than x squared. So you're not going to get things like squares of primes or products of primes. You just basically just get primes. And the number of such primes is something like y over log x. And if you want x over log x survivors, then again you get stuck. You get back to y being the same as x. Okay, so the simple Eratosthenes doesn't work. It doesn't get you better than y size x, and randomly choosing progressions doesn't do this. But it turns out that a certain combination of the two does. So it turns out that this sieve is actually quite inefficient. You don't need to spend all the primes up to x in order to get this type of effect. If you only take primes between say x and what did I? Let me just double check what I. So yeah, if you only take primes up to some thresholds, if you only take primes that are very large or primes that are very small, so okay, it turns out that there's a okay. If you knock out 0 mod p for really small primes or large primes, and this z is something between x and log x, it turns out that the optimum value of z turns out to be something a bit weird. X over log x over 4 times log x turns out to be a good choice. This is not obvious to begin with, but something between x and log x. If you take large primes and small primes, so from all the primes between 1 and x, you use a simple Eratosthenes primes between z and x, and also for small primes, 1 up to say log the 10x. Then if you apply the same procedure, so you don't do anything for the medium primes yet, what you get is that you still get the primes between x and y, but there's a few more survivors, but not many. If you knock out the numbers that are not divisible by any prime between z and x, and also not divisible by any small prime, what you're left with what are called the z-smooth numbers. Okay, these are numbers whose prime factors are all less than z. Okay, these are the only numbers that will survive this procedure of removing all the 0 mod p's between z and x, other than the large primes. There's also large primes times very small numbers, but also sitting out the 0 mod p's down here. This is meant to kill those. So it turns out that smooth numbers are very rare. It's very unusual for a number to only have very small prime factors. Most numbers have at least one large prime factor, and there are standard estimates for how often numbers smooth. And it turns out that if you pick this particular choice of threshold z to define what smooth means, then this set is much smaller than this set here. It's quite a bit smaller by many factors of log x. So much so that it's basically negligible. So if you pick this specific value of z, it turns out that these smooth numbers basically are irrelevant. And you could in fact just remove them it's part of just put them in as part of the survivors. So the thing is, you don't need to use the simple Eratosthenes for these medium primes, and you still get about y over log x survivors here. So then what Rankin did in modern language is that he just picked random residue classes here. Okay, so we have all these extra residue classes left over, and basically you just sort of just shoot randomly, and you can refine this. The upshot is that you get to divide out basically by a factor 1 over log z. you get to randomly shoot a whole bunch of these primes, and then you just get sort of a random subset of the primes as your survivors. And for this particular choice of z, you can get this down to x for log x if so by this method, Rankin was able to get y to be about log x. He could make this method work. Okay, for y as big as this quantity, which is for how he got this bounded with the square down here. Okay, so yeah, he did a combination of specific Eratosthenes and some random residue classes. Okay, so what in 5 minutes remaining? So what was our contribution? In our setting, we had a slightly larger value of y, and so when we did this, so after all this procedure, so Rankin's procedure gives you a random set of primes size by x log x, which is what we want, times some extra factor, I think log x, roughly. Okay, so this additional unwanted factor of log x that we wanted to eliminate. So what we did was that we again spent a little bit more money, okay, and introduced some more primes between x and 2x. And we wanted to use the primes between x and 2x to cover this set, or at least cut the set down to the size of about x for log x. Okay, now, previously, what we did was that every prime here can be used to knock out one prime in this, one of these survivors. Okay, but that only would work if you had about x over log x survivors. Here we have a bit more than x over log x survivors. So what we need, in order for this to work, okay, we need to find residue classes. AP mod P that hit not just one prime here, but hit many primes. Okay. Okay. So you want a single shot to knock many ducks down at a time, not just one duck at a time, rather than one. Okay, so we want to find arithmetic progressions that contain a lot of primes. So until about 10 years ago, there was no way to do this. And this is why Erdős was prized, and so why we stuck for 10 years. But then in the early 2000s, there were two ways emerged to start creating, to find residue classes that contain primes. So one was the progress of linear equations between primes, where so the work of Ben Green and myself and other people allowed us to find things like arithmetic progressions of primes. And that technology is one way which you can start finding residue classes that hit many primes at once. But the bounds are not very good. We were able to improve the Rankin bound by a little bit, but not by this log law. But then this is the result of Maynard on short intervals between primes. So we saw in the last lecture that you could create, using these sieves of Maynard and Gaussian pendulum and so forth, you can find short intervals that contain at least two primes, right? And that's because of shortcut between primes. But in fact, the same methods actually not just gives two primes, but they can give many primes. So the methods of Maynard could actually find progressions of some length k that contain about log k primes. That you could actually get the number of primes to go to infinity. And it turns out that a modification of those methods lets you find lots and lots of residue classes AP mod P, which contain many primes. You can make them contain about log many of the primes in this set. So you can actually find clever ways to sort of shoot your gun so that you can knock out many ducks at a time. So that is this log game, which is in principle how you get to this point. Now, there's one final technical issue, which is that once you do this, you can find lots of different residue classes, each of which takes out a certain number of survivors. And ideally, all these sets of survivors that you remove are disjoint. If they're disjoint, then you're being very efficient, and you will eliminate most of your survivors quite in sort of the optimal amount of time. But there's this one remaining enemy, which is that maybe you're shooting the same depth over and over again. Okay, so you're finding lots and lots of residue classes which remove survivors, but you're always moving the same set of survivors, and you're not actually reducing the total number of survivors too much. So that's a problem. And so initially, in Maynard's paper, for example, he got around this by sort of selecting these risk classes randomly and using some independence. But the things that if you shoot randomly, even randomly, there's sometimes some survivors. Sometimes there's an overlap between these sets that you're removing. And so in order to get our full result with sort of the best savings of log and so forth, we needed to use some of the results from combinatorics. So there are these covering results from combinatorics called hypergraph covering, hypergraph packing theorems, where the situation is maybe you've got a set of n elements, and you've got all these collections of, say, k element subsets. Okay, so maybe you have a big set of n elements, okay, and then you have all these little sets of k elements each. And you want to remove a whole bunch of these sets so that that you cover most of the set. Maybe you only leave, say, epsilon n survivors. Okay, so you want to cover all but say epsilon n of your original set by k element subsets. Okay, so ideally, if you can make all these sets disjoint, ideally you can do this using about n over k sets. Okay? If there's no overlap between the sets you remove, you can cover very efficiently. But there is some overlap. And if you sort of select these k element sets randomly, there's enough overlap that if you want to only have epsilon n survivors, you lose an extra log factor. If you want to really annihilate all but epsilon n survivors, just some sort of random waste. But there's a technique which is better than the random method. It's called the semi-random method. It has a lovely alternate name. It's also called the rodal nibble. That there's actually a smarter way to remove k element subsets from n element set, which makes the sets more disjoint. So what you do is that rather than take all the sets out at once, you take a small number of sets out at once. So you take a small bite, a nibble, out of this set. So you take maybe epsilon times n over k of these sets out first. And if you want to take a small number of sets out, then there isn't that much overlap between them if all the parameters are chosen correctly. So it's very efficient initially. So you take a small nibble, and then you remove the sets. You take away all the sets that you've nibbled out, and then any k element set that intersects the sets that you've already eaten, you also remove. So you then, so that all the k element sets remaining are just concentrated in the surviving set. And then you repeat the process again. Take it. So you nibble, and then you refine your collection sets, and you nibble, and you do that. And it turns out that this procedure can be controlled under various hypotheses on this k element set, every kind of uniformly distributed, and so forth. And that gives you almost near optimal packing, where you don't lose this log factor. Yes?
You remove also the same survivors, even with this method?
Yeah, I mean, you pick a small number of k element subsets, you remove those survivors, and then you throw away also any k element sets that intersect
of the same survivors.
It's a random procedure, which is different from the naive random procedure. So it will generate a different set of k element sets to cover than you would have if you did it. It's an existence theorem. So the conclusion of this type of result is that there exists a way to remove about n over k sets from this big set of size n in such a way that only like epsilon n elements remain. But the specific sets that are constructed this way is a different construction than if you tried just a naive, like greedy algorithm or a random algorithm. So it's a smarter algorithm that gives you a different set of sets to remove, and it gives you a different set of survivors, but it will end up being smaller, a smaller set of survivors than other methods. So this is a massive oversimplification of this strategy, but there is a general combinatorial hypergraph covering theorem, basically due to Pipitcher and Spencer, that implements this. And by using that combinatorial tool, we were able to make this method very efficient, and it gives us pretty much the optimum limit of this method. And in order to do any better, you either have to improve the Maynard sieve and find not just progressions that contain log x primes, but predict progressions that contain more primes. So we either have to improve the Maynard sieve, or we have to find a completely different way to generate strings of consecutive numbers that don't come from the Chinese Maynard theorem, which is actually a rather inefficient approach. The Chinese Maynard theorem only works if you knock out numbers that are divisible by small primes. A number could also be composite because it's divisible by quite a large prime. But you can't really use really large primes in this analysis because the Chinese Maynard theorem won't work past a certain point. But this is the best we can do with current technology. So I will stop here.
Very interesting county fairs you must have in Adelaide. Anyway, are there any questions? Yes?
Yes, so thank you very much. Maybe I missed it, but you explained very carefully how you use the big primes between Z and X. Mm-hmm. Where are these small primes between 1 and the 10th power of X?
Oh, okay, so it's a technical thing. So right. Okay. So if you only use 0 mod p for large primes, then the survivors actually what you get is that you on the one hand you get C-smooth numbers, but you can also get primes bigger than x between x and y. But you can also get products of primes like p times a C-smooth number. Where p is between x and y. So for example, you can get twice a prime or 3 times a prime. And those numbers would also survive this type of procedure. So that's annoying because there's quite a lot of, if you had those survivors, then you have a much larger set. But yeah, the purpose of also knocking out the small primes is that it basically knocks out all these extra numbers. This number is just anything bigger than y over x would work here. That if you yeah, so a large prime times a small number can also happen, but that small number will be divisible by one of the primes up to here. So yeah, we just spend some of the very small residue classes to eliminate that possibility.